Okay, good afternoon, everyone. So, in the last lecture, we were discussing binary number system. Just a minute. Yeah. Okay. So, what did we see? We saw that suppose if you have only one wire or say one cell to store the information, and if your number system has only 2 digits, so you have only 2 options, right? Either 0 or 1. If you have 2 wires, you can store 4 numbers, right? So make a distinction between digit and number. Number can be made up of multiple digits, right? We know decimal numbers are made up of 10 digits, 10 different kinds of digits, 0 to 9, but the number can be of any length, right? Similarly, binary number can be of any length, but the digits are only 2, 0 and 1, right? So if you have only one wire, you have only 2 options, 2 digits or 2 numbers. If you have 2 wires, you have still 2 digits but 4 different numbers. If you have 3 wires, then you can have 8 different numbers. If you have 4 wires, you can have 16 different numbers, right? If you have n wires, you can store 2 power n different numbers, right? So the more wires or the more cells in your RAM you have, the more data you can store, and the more varied kind of information you can store, right? So that's what we saw. And we also looked at the binary number system. So decimal system, we all know, we have ones place, tens place, hundreds place, thousands place, and so on. They are powers of 10. So it starts with, from the right, it starts with 10 power 0, 10 power 1, 10 square, and so on. And each place will have a digit. So you multiply that digit with its corresponding place value, and you add up all these products, you will get the final number. In decimal system, whatever is the original number, you will get back the same number. Whatever is the input number, you will get back the same number as output. That is decimal system. But in other systems, the digits are different, because in decimal system you have 10 digits, 0 to 9, but in binary system you have only 2 digits, 0 and 1. In octal system you have how many digits? 8 digits, 0 to 7. In hexadecimal you have how many digits? 16, 0 to hexadecimal. I can't understand a bit. 0 to 9, 8 to 11. Yeah, 0 to F or 0 to 15. 15 is a number, but it is represented using a digit or a symbol called F. Okay, so you have 16 different digits, so-called digits. So any decimal system, or sorry, any number system you take of base n, you will have n digits from 0 to n minus 1. Okay, so that's what we saw. Now in binary system, suppose the number is 1100, but the place values in binary system will be 1s, 2s, 4s, 8s, 16s, and so on, right? And the digits will be either 0 or 1. So all you need to do is take each digit, multiply it with its respective place value, and add up all these products. So you will have 0 into 1 plus 0 into 2 plus 1 into 4 plus 1 into 8, right? So the output will be 12. Okay, so here the input number and the output number are different because their number systems are different. They are equivalent, but representations are different. It is represented as 12 is represented as 1 2 in decimal system, 12 is represented as 1100 in binary system, 12 is represented as say XII in Roman system, right? So the representations are different. All right. This is another example for say 1001, again a binary number. You apply the same method. 1 into 1 plus 0 into 2 plus 0 into 4 plus 1 into 8, you will get 9. For binary system, the simple method is ignore all the place values with zeros, consider only the place values with 1s, add the place values. So in this case, 1 units place has 1, 8's place has 1, so add 1 plus 8, 9. That's it. You can just ignore the place values with zeros. Okay, so this is how it is done. This also we saw. Suppose if I have 32 wires, if all the wires have 0, then what is the value of that entire number, 32-bit number? 0. If all the wires have 1, then the value of the 32-bit number, say in powers of 2, will be 2 power 32 minus 1, right? That's the maximum number that it can store. So the range of numbers is 0 to 2 power 32 minus 1. But the total number of numbers are 2 power 32. Right? Always keep this in mind. If you are in doubt, get back to decimal system. If you have 3 digits, the maximum number is 999. The maximum number is not 1000. But the total number of numbers which you can represent in decimal system using 3 digits is 1000. It is not 1 to 999, it is 0 to 999. So you are able to represent 1000 different numbers using 3 digits in decimal system. Alright? This also we saw text in binary. If I want to store text in the computer, what do? I take all the different possible characters in my text. I give a number to each character, and whenever I see this character, I take the corresponding number and convert it to binary. Right? That's how I store text. So it is already encoded because it needs to be standardized across the world. So it is standardized and it is called ASCII. We saw the table, ASCII table. How many characters are there in this table? 127 or 128? 128, because it starts from 0 and goes up to 127. Now, how many bits you need to store 128 different values? 7 bits or 8 bits? 7 bits, right? Like I said, if you have n bits, you can store 2 power n different values. Same question in reverse. If you want to store 2 power n different values, minimum how many bits you need? N bits. Here, what is 128 in powers of 2? 2 power 7. So if I want to store 2 power 7 different values, how many bits I need? 7 bits, right? So using 7 bits, I can store 128 different values. These are all characters, both printable and non-printable characters. Like ABCD, they are printable, you can see them, but non-printable characters are like enter, you can't print it, or backspace. These are non-printable characters, but they need a different number. So you have to store them also, right? So all the keys on the keyboard and even more, they are sort of stored here. Okay. Now 7 bits are sufficient, and then we also saw there is something called extended ASCII. One more bit is added, 8 bits, and then more characters are mapped to it, right? So these are characters which you either use more frequently, or they are characters which are in languages whose whose notation looks closer to English, maybe French or European languages. You have some marks over the letters to differentiate the pronunciation, that kind of thing. So they are all covered within. Now, how many total characters are there here? Total values, symbols? 255 or 256? 256, right? Start from 0. So 256. So how many bits are necessary? 8 bits, right? So using 8 bits, you can store 256 different values, and all these values can be represented using 8 bits. Fine. We will see why we need 8 bits. I discussed sort of partial reason in the last class that you need a sign bit. Suppose if you want to store negative numbers. Say if I want, the previous ASCII table does not have separate values for positive numbers and separate values for negative numbers. Like +4, -4, +3, -3, there are no separate values. It only has values for positive numbers, 0, 1, 2, 3, and so on. They are not even numbers, they are just digits. They are like character. Okay. But if I want to represent -3 or -5 or -100, whatever it is, how do I do that? One option is I have 7 bits to represent the magnitude. 1 bit I will reserve as a sign bit. So I will need minimum 8 bits. 0 means positive, 1 means negative. That is one way. But then that sign bit is necessary only for digits or numbers. It's not necessary for alphabets. -a, -b doesn't make sense, right? So why wasting that bit as a sign bit even for characters? That bit can be a sign bit for numbers, but for characters, that bit is wasted if you use it as a sign bit. Instead, use that bit also as part of the number, 8-bit number, and represent something more with it, right? So then you will get extended ASCII. So now using extended ASCII, how do we represent negative numbers? We will see that later. Yeah. So what I'm saying is, if you see the previous ASCII table, there are mappings for digits. Like you see 48 stands for 0, then 49 stands for 1, and so on, right? So if I want to represent 0, 1, 2, 3, 4, I have 48, 49, and so on. But if I want to represent -3 or -5, how do I do that? There is no option here. There is a number for hyphen, but putting hyphen and this number together does not make it a negative number. It just makes them like two characters beside each other, like AB. This will be like hyphen and that number, right? So it is not treated as a negative number by the computer. They are just two characters put beside each other. So for me to capture negative numbers, one option is now all these numbers will fit in, all these characters will fit in 7 bits. What I will do, I will add an additional bit which I will treat as the sign bit. I have only two signs, positive and negative. So I just need two values, 0 and 1. I will just assign 0 means positive, 1 means negative. So first bit is my sign bit, remaining 7 bits are my magnitude. Now this is okay, this works, but this additional bit is useful only when I am dealing with numbers, say 0, 1, 2, 3 and so on. But if I am dealing with characters, A, B, C, D, they will also come in 7 bits. This extra 1 bit, it is wasted. Plus or minus, giving meaning of plus or minus to this extra bit doesn't make sense for characters. So rather than that, if I can use this additional 8th bit instead of using it as a sign bit, if I can use it also as part of the bigger number, then it will be useful to you. So that's what extended ASCII does. So that will handle both these cases. It will handle negative numbers. It will also handle additional characters. So we will see that. So we won't have a separate sign bit as such, but still we can handle negative numbers. You will see that later. Okay. So basically any text, storing any text in computer is easy. You take each character, find its corresponding ASCII value, that is a decimal number, convert the decimal number to binary. That's it. So you store the text in the form of binary. Finally, everything should be converted to binary. That's the idea, right? Now, what about images? Text is fine. You map each character to a number, convert that number to binary. What about images? Okay, color. How do I convert color to binary? Pixels, fine. How do I convert pixel to binary? RGB. So how do I convert RGB to binary? So what is RGB? Red, green, blue. So how is red, green, blue specified? Fine, hex code, binary, whatever that is. But what is the range of each of these colors? What is the range of red? What is the range of green? What is the range of blue? 0 to 255. Exactly. So red ranges from 0 to 255, green ranges from 0 to 255, blue ranges from 0 to 255. So it's a triple. In this triple, each value ranges from 0 to 255. Combination of these different values will give you different colors. Okay. So this image looks continuous to us, right? But basically, what is it made of? It's made of pixels, right? So imagine. Okay. Now, what are pixels? Whatever is your screen size, it is basically divided into some squares, right? So the more number of squares you have, the more clear the picture quality is. So whenever you hear of resolution, that is nothing but the number of pixels that are there in your screen. So when you hear of HD resolution, full HD resolution, ultra HD resolution, all these things, it means more number of pixels are fit within the same space, right? Now within this screen size, there may be 2000 by 1000. It doesn't matter exact number. It's like 1080 by something, right? So those many pixels, one along the width, another along the height. Okay, so 1080 by say 960 pixels, something like that. Or if your screen is of square shape, then you will have 1080 by 1080 or something like that. Now within the same size, if you have more pixels, I can fit more pixels also. Then the pixels will be smaller and more information can be packed within the same space. Then how will it look? It will look more closer to the original figure, right? Like these are pixels within the same space. The first one has less pixels, second one has more pixels, third one has even more pixels. But the third one looks more closer to a circle because it has more pixels, right? So the more denser, the more pixels you have, the more denser your information is, and the more closer it is to the original image, right? Say this is another example. You see less pixels, more pixels, and even more pixels. The first one, you won't even notice that it is made up of pixels, the top one, unless someone tells you, right? But the bottom one, even if you don't want to, you will notice pixels. So that is what we call as pixelated image, right? The image is not clear. You are seeing a lot of, rectangles, squares, all those things. All right. Now, if the image is only black and white, then how do we store it? Suppose you don't need RGB. It's only a grayscale image, black and white. Then do you need RGB values, 0 to 255, all those things? No. How do you store it then? Yeah, that's it. You store it as a matrix, and each matrix in each cell in the matrix is either black or white. If it is black, you say 1. If it is white, you say 0. So this is a matrix which is just made up of zeros and ones, right? So this is an example. So that image is stored as zeros and ones like this. Whichever cell has black in it, that corresponding cell is stored as 1. Whichever cell has white, that corresponding cell is stored as 0. You don't need any more values, right? So wherever you have just binary values, just do it with zeros and ones. If you don't have binary values, if you need to deal with more values, then it should be more complicated. Then you get into decimal numbers, right? Fine. So grayscale images or black and white images can be stored directly using zeros and ones. You don't need RGB values there. But colored images, you can't just use 0 and 1. Like if you see this image, there are different colors or different shades of the same color, off-white, green, gray, greenish yellow, So different kinds or different shades of the same color. So you have a spectrum of millions of colors. Now I want to store millions of colors. 0 and 1 can't handle that, right? How do I store these different, this wide gamut of colors? For that, I use RGB values. So red, green, blue are the primary colors. Using these three, mixing these three in various proportions, I can generate any color, right? I can generate millions of colors. So this is how the pixel grid is basically stored. Any image you give, it is made up of colors, and it is made up of pixels. So each pixel has a location or has a coordinate, right? So suppose I want to locate this pixel. Its coordinate is 1, 1, right? And its value is yellow. Yellow is made up of red and green. So red is 255, green is 255, blue is 0, right? Suppose I want a pixel with only pure red. Then how will the triple look? 255, 0, 0. Pure green, 0, 255, 0. Pure blue, 0, 0, 255. Right? Here, this blue and this green are not pure. They are some variant of blue and green. Okay, that's why here the values are not, other values are not zeros. But you have some constant value and 255 here. Okay, and similarly this green here, it's not pure green, but closer to green. That's why you have 181 here and other values are less. Fine. So this is how you get different colors. Different combinations of these numbers will give you all different possible colors. Fine, as simple as that. Okay. So another example. So suppose this particular color, if I want to represent, it is 253, 78, 141. Okay. So red is 253, green is 78, blue is 141. Right. So each pixel is nothing but RGB values, and RGB values themselves are decimal numbers, and these decimal numbers in turn can be converted to binary numbers. So in the previous case, it is one number, each character is one number, that number can be converted to binary. In this case, each pixel is a triple, so that you can store as an array, and in this array, each number you convert to binary, right? What about video? Yeah, video is what? Yeah, video is nothing but series of images. It is like minimum 24 frames per second. What is a frame? Frame is nothing but image. So when I play each image or when I play this series of images at minimum speed, and that is minimum 24 frames per second, then it seems like a video to me. It seems like a moving image to me. So video is nothing but images. So video will be broken down into image, image will be broken down into pixels, pixel is broken down into RGB values. Each RGB value is a decimal number, that decimal number will be converted to binary number. So if an image is a series of pixels, a video is nothing but a series of images. That's it. Right? A video is nothing but a series of images or frames. So in each image you have millions of pixels. Now in 1 minute video, for 1 second we have 24 frames, minimum 24 images. So 24 into 60, for 1 minute you have so many images and each image has so many pixels. So you will have billions of pixels in 1 minute. Okay. So again, everything is boiled down to numbers. As simple as that. Everything can be boiled down to numbers. What about audio? Yeah. Each frame, video is broken down into array of frames. Each frame is a matrix, which is again like an array of numbers. Each number is a triple, which is again like an array of numbers. Now each of those numbers you convert to binary. Okay. Yeah. What about sound? How do you convert sound to numbers? Basically, everything you should convert to binary. How do you convert sound to binary? Frequency, high pitch, low pitch. Yeah, fine. But first of all, sound is a continuous signal, right? It's a wave, it's a continuous signal. Can you store a continuous signal in a computer as a continuous signal? Yes or no? No. Why? But when we hear, like when you play sound, it is played continuously, right? It's not played in a broken fashion. So why do you say it is not stored? It can't be stored. What do you mean by continuous signal? Sorry, loudly. No interval. Not exactly. Interval is what you choose. From this to this, this is the portion of my signal. Interval is up to me. Yeah. What do you mean by continuous signal? No break. Okay. So in mathematics, how do you differentiate a continuous signal from discrete signal? Sorry. Loudly. Then by using limits. Okay. All right. So now, do you know? I mean, you will be knowing what is a differentiable curve and what is not a differentiable curve. Differentiable function and what is not a differentiable function. What are the conditions for a function to be differentiable? Limit should exist. What do you mean by limit should exist? In common man's language, can you explain? Forget limits. Exactly. No sharp turn. It should be smooth. First, there should be no gaps. Second, even if there are no gaps, it can be rugged or it can be like sharp turns. That should not be there. It should be smooth, right? You know step function, right? So there are actual steps, discrete steps. It is continuous, but it is not smooth. So it is differentiable at some points. It is not differentiable at other points, right? But if a function is smooth and continuous, only then it is differentiable in layman's terms. Fine. Continuous means it is like a real number line. What defines a real number line? Or what is the defining characteristic of a real number line? What is the difference between real numbers and natural numbers? Or what characterizes a real number line or real number plane? Huh? Continuous, yes, yeah. It includes all the values. Natural numbers also include all values. Real numbers all include all real numbers, natural numbers include all natural numbers. So both systems include all corresponding values. So that is not telling you the difference. Real numbers are what? Real number system or real number line, that defining characteristic is between every two real numbers there are infinite real numbers. Between every 2 points there are infinite points. Right? So it is fundamentally an infinity. It's an infinite thing. Can you store infinity in a computer? Can you store infinite things in a computer? No matter how big the memory is, no matter how big the memory is, infinity is much bigger. Infinity is much bigger than whatever large finite number you can think of. No matter how large the finite number is, it is still finite. It is always smaller than infinity. So you cannot store infinite numbers, or even one number, the decimal expansion can be infinite, right? Like pi or any irrational number, the decimal expansion is infinite. Can you store the entire irrational number in a computer? No. Even in a supercomputer or any computer you take, you can't store the entire irrational number. You have to cut it somewhere, right? So the point is, the memory in a computer is limited, no matter how big it is. But infinity is unlimited. So continuous signal is like infinity. You cannot store a continuous signal directly in a computer. You have to break it, or you have to convert it into a discrete signal. That's what we call as digital. Digital signal, analog to digital. So you have to convert it to a digital signal because a computer can only deal with digits, and it can store only digits. It can store only discrete values. It can't store continuous values. It can't store infinite values or infinite points between every 2 points. It can't store all the points. It can store only some points. Fine. So what do? We break the continuous signal into samples. So what we call as sampling. Okay. Before that, so how is sound produced and stored? So you speak, sound waves are generated. They are converted to electrical voltage, and this electrical voltage is an analog signal. So what do you do to store it in computer? You have ADC. What is ADC? Analog to digital converter. So they are converted to zeros and ones. Now whatever processing you want to do, you want to amplify it, you want to remove the noise, you want to do anything with that sound signal, you do it at this level, zeros and ones. And then you recreate the analog signal. What do you use for that? DAC, digital to analog converter. And that you hear as sound waves. Fine. That's it. So you have to convert a continuous signal. You have to break it. You have to take minimum number of samples and store those samples. Samples are discrete. These discrete things can be converted to digits. You can store those digits. Now you may ask, okay, but it is infinite. How many samples should I take? And will there be no loss of information? Right? So there is something called sampling theorem, which tells you if you take minimum these many number of samples, you can recreate the original signal from the samples. All right. So that you will probably learn in your electrical signals course. So you have a continuous signal, you take the samples, fine. Now, how many samples we should take? The more samples you take, the closer it will be to the original curve, right? So to store more samples, you need more bits. So a 32-bit machine will store more information of the signal rather than an 8-bit machine. All right. Again, it's like pixels, resolution. The more pixels you have, the more closer it will be to the original image. The less pixels you have, the farther away it is from the original image. Similarly, the more bits you have, the more samples you can take, and the more closer it will be to the original image, original signal. The less bits, the farther it is from the original signal. That's all. Okay. Finally, it is a discrete thing, and that discrete thing is converted to digital. Fine. The entire analog signal or the entire continuous signal cannot be stored in a computer. Okay. Okay. So anything can be digitized as long as it is information. Anything you can think of. Numbers, textual documents, images, videos, audio, bank transactions, web pages, and almost anything you can think of. Except very few things which are like, beyond the boundary of science, or, they get into the realm of philosophy. Otherwise, most of the things which you can think of in this world, in this universe, if they can be mapped to numbers, and most of them can be mapped to numbers, and hence they can be digitized. They can be converted to binary at the end. Okay. So information is resolution of data. So what do you mean by resolution of data? So imagine data is like a person. I take an image of that person. Now this image I can store using some 1000 pixels or 1 million pixels or 1 billion pixels. This is my resolution, right? The data is that person. But what is information? The way I capture the data, at what granularity I capture the data, with what resolution I capture the data, that is the information. So basically the digital way, the digital representation of the analog information, this digital representation always has a resolution. You can store it at high resolution or low resolution or further low resolution. The granularity with which you store the analog data, that granularity is called resolution. Okay? So data with resolution or data with granularity is information, which means digitalized data is information. Okay, that which can be converted to numbers, decimal numbers, and in turn binary numbers. So information in binary form is convenient to deal with, right? Because it is easy to design machines that work on binary data. So information processing is nothing but binary operations, because entire information, whatever kind of information you take, text, audio, video, any kind of information you take, it has to be finally converted to bits. And once it is converted to bits, you can work only on those bits. So whatever processing you want to do, you have to do at the level of bits, zeros and ones. You transform them, you flip them, you delete some of them, you add, you do some addition, subtraction, multiplication, whatever it is, you are doing at the level of bits. So binary operations, entire information processing has to be done using binary operations. That's it. There is nothing outside binary operations through which you can do information processing. Because entire information is binary, whatever operation you have to perform, whatever processing you have to perform on this binary data, and all those operations are binary operations. Fine. So these are like equivalent. Information processing in a computer is nothing but binary operations. So computation is another word for information processing. This aligns with what I said earlier in the previous lectures, that computer is like a black box which takes some input and gives you some output. Whatever is happening inside this black box is information processing. That's it. And what is information processing? Processing binary data, processing zeros and ones. So you need to understand how to handle zeros and ones, how to handle bits, what kind of operations you can perform on bits. See, one is data. Second is the operations you can perform on this data. We just looked at data, how data is stored, how to convert decimal to binary, right? All this we saw. Later we will see what kind of operations you can perform on this data. You see, on different kinds of data, we can perform different operations, right? Say, for instance, this table is there. I can place things on that. I can't eat it, or I can't read it, or I can't write it. It doesn't make sense to attribute these kind of actions to that, right? So different objects will allow you to perform different kinds of actions on them. Similarly, bits will allow you to perform some kind of operations or actions on them. Okay, so depending on the data, your operations will be defined. Okay, like I said earlier, characters, it doesn't make sense to assign sign value to them, positive and negative, but for numbers it makes sense, right? So one operation you can perform is to convert positive to negative or negative to positive, but you cannot perform an operation like convert positive character to negative character, positive alphabet to negative alphabet. It doesn't make sense. So those operations you cannot perform on some data. Okay, so on zeros and ones, what all operations you can perform, that we will see later. All right, so before we move on to the next section, let me take attendance. So please open your phones. Okay. I don't know why my mouse is not working. Just a minute. Okay. In case you are having any issues, don't come to me. Send me an email, and I'll forward it to ERP. Okay. One last time. Okay, if it is done, it's done. Otherwise, just drop me an email. We'll look at it later. Let's not disturb the class. All right. So let's move on. Okay. So there is some problem with my digital tablet. So I will be using my earlier notes last year's. So you will understand as we proceed. So, all right. Okay. Now let's imagine, suppose there is a hypothetical mapping. We are not following ASCII mapping. Let's assume some hypothetical mapping. Say I map 0 to 0, A to 1, B to 2, C to 3, and so on. All right. And say 26 letters to 26 numbers, and then space I map to number 27. Fine. Now each of these will also have the corresponding binary mapping. A's binary value will be 1, B's binary value will be 10, C will be 11, and so on. Right. Now, suppose if I want to send you the text AB, right? How do I encode it in binary? I will take each character's binary value and I will write them beside each other. I will send you that binary text. A is 1, B is 10. So I send you 110. I am sending you only binary. I am not sending you anything else. Fine. Now, if I want to send you F, what is F's binary value? 110. Now, both AB and F are mapping to 110. Okay. Now, when I send you 110, how will you know whether I am sending AB or F? How do you decode it? Encoding is the English text that I want to send you. I am converting it to binary. So that is encoding English text into binary. Decoding is from this binary you should be able to regenerate or derive the English text that I want to send you. Now, I am only sending you 110. I am only sending you the code. How do you decode it? This 110, if you decode it in one way, you will get AB. If you decode it in another way, you will get F. But that is not good, right? The information is getting, corrupted in some sense. I may be sending you AB, you may be thinking it is F. Or I may be sending you F, you may be thinking it is AB. So how do we ensure that my meaning is communicated to you in an unambiguous way? How do I remove this ambiguity? Why is the ambiguity coming? Can anyone sort of paraphrase it in a formal way? Like, why is the ambiguity coming? In encoding, there is no ambiguity. I am starting with AB, there is only one way to encode it. 110, done. I am starting with F, there is only one way to encode it. 110, done. But while decoding, there is ambiguity. Why? Okay, set number of bits for each letter. Fine, that is the solution. But what is the problem? Can you explain the problem? Both? Yes, both have same number. So what is happening here? Two or more elements are mapping to the same output, right? So in terms of functions, if you think in terms of functions, when can a function have an inverse function? Yeah? Exactly. Only when the function is bijective, it can have an inverse. If the function is not bijective, it can't have inverse. Same problem, right? If two or more elements are mapping to the same output, right? The function is fine, it's a function, but it cannot have an inverse because when I start from the output and I try to derive the input, I am confused. Which input should I take? I have two options, or I may have three options, 10 options. Which of these options should I take? I don't have one option. That is the problem because there is many to one mapping. But if there is one to one mapping, X is mapping to Y, F inverse y will be x. But if x1 and x2 are mapping to y, then F inverse y will be what? Is it x1 or x2? I'm confused. So that is the confusion which is happening here. This is a many-to-one function. It is not a bijective function. So what should I do? Yes. So I need to convert this many-to-one function into a bijective function. How do I convert it to bijective function? He gave an answer. Any other answers? You see, you take this example here. This 110 I am sending. Now this 110 can be decoded in multiple ways. One is, suppose I treat this entire thing as one unit. This entire thing as one number. Then what will this number map to? 110 is 6. 6 is F. Another way is I don't treat this entire string as one number. I will break it. I can break it in two ways. One is I take 1 as one part and 10 as another part. So 1 will map to A, 10 will map to 2, that is mapping to B. So AB. I can break it in another way. I will take 1 as one part and 0 as another part. So 1 means 3, 3 is mapping to C. 0 is mapping to 0. So that will mean C0. Now you see, depending on how you interpret this same string, depending on how you break it, whether you break it or not, I don't know whether should I treat this entire string as one unit or should I break it into further units, and if I have to break it, how do I break it, where do I break it? Depending on how I treat this input or how I treat this binary string, I will get different answers. If I don't break it, it will map to F. If I break it in one way, it will map to, actually I can break it into three parts also. I can break it into two parts or I can break it into three parts. If I break it into two parts, I can break it as one part, 10 as another part. Another way is 1 as one part, 0 as another part. If I break it into three parts, 1 is mapping to A, again 1 is mapping to A, 0 is mapping to 0. So I am getting A0. So in fact 4 outputs are there. AB I didn't show. That is another output. That is another decoding, right? So depending on how I break it, I am getting different decodings. So I don't want this ambiguity, right? So to remove this ambiguity, what should I do? Storing different bytes. Okay, yeah, fine. That is similar to the answer he gave. So we'll come to that. Just one more example. Suppose if I want to send you A space B. Now space value is 27. Its corresponding binary is what? You convert that 27 to binary. How do you convert a decimal number to binary? Continuously keep dividing it with 2. Okay? At each step you will get a quotient and a remainder. Once you are done with the entire division, trace the remainders in the reverse order. So the remainders are 1, 1, 0, 1, 1 from bottom to top. So that is the corresponding value of 27. So now, if I have to send you A space B, what do I do? A's binary value is 1. Space binary value is 1, 1, 0, 1, 1. B's binary value is 1, 0. I am sending you the entire string. Now, my intention is for you to read it as A space B. But you only see the string. If you break it in any different way than the way I sent you, you will get a different output. So instead of breaking it the way I sent you, you broke it in a different way. Say you group first two ones together, then 1, 0, 1 together, then a single 1 and then 1, 0. So two ones together, that is 3. 3 is mapping to C. Then 1, 0, 1, that is 5. 5 is mapping to E. Then a single 1, that is mapping to A, and then 1, 0, that is mapping to B. So I sent you A space B, but you are getting CEAB because you didn't break it the way I intended you to break it. So this confusion is there, right? So to avoid this confusion, a simple method is you fix the number of bits that, or you fix a chunk size. You sort of say, you write a rule, okay, you need to read these many bits, this block of bits at a time. You need to read whatever that block is. It can be, you need to read 4 bits at a time, or 8 bits at a time, or 10 bits, or 20 bits at a time. Whatever it is, you have to read one block at a time. And you have to read this block as the basic unit. Okay, so let's look at that. So what is the solution? By having fixed chunk size. So let us assume the chunk size is 4 bits. Okay, it's not 4 bits in computer, it's 8 bits, but let's assume it is 4 bits. If my chunk size is 4 bits, then how do I specify F? F is 6. 6 is 110. But since I have to use 4 bits, I will write 0110. I will fill the remaining bits with zeros, the leftmost bits. Okay, so if I have to send F, I will send 0, 1, 1, 0. If I have to send AB, what do? A should have 4 bits. Although A is 1, I should fill the remaining 3 bits with zeros. Similarly, although B is 1, 0, I will fill the remaining 2 bits with zeros. So B is sent not as 1, 0, but as 0, 0, 1, 0. A is sent not as 1, but as 0, 0, 1. So if I have to send AB, I will send this 8-bit string 0, 0, 1 and then 0, 0, 1, 0. Right? So now you will clearly know that when I am sending 8 bits, I am sending not 1 character but 2 characters, because each character has only 4 bits. And when I am sending F, I am sending only 4 bits. So you will know I sent only 1 character. In the previous case, when I sent you 110, you don't know whether I sent you 1 character or 2 characters or 3 characters. But now, if I am sending you 1 character, I am sending you only 4 bits. If I am sending you 2 characters, I will send you 8 bits. If I am sending 3 characters, I will send you 12 bits. Right? So, the only disadvantage with this is, can anyone tell me? Memory wastage. Right? Say for A, I need only 1 bit, but I am using 4 bits of space. Similarly, if you are using 8 bits, if you are sending A, suppose if its ASCII value is 1, you are wasting 7 bits. You just need 1 bit to send A, but still you are wasting 7 bits, right? So it's a trade-off. There is no other option. You have to make a trade-off. If you keep too many bits than needed, there is a lot of memory wastage. But if you keep too few bits than needed, then you cannot represent sufficient variety of information. Suppose if I have only 2 bits, then I can represent only 4 different characters. But I want to represent 255 different characters or 256 different characters. Then I need minimum 8 bits, right? But just to represent 256 different characters, if I use 16 bits, 8 bits are always wasted. Okay, so this is the trade-off. So after a lot of experimentation and all that, people found that most used characters can be actually stored in 7 bits. Okay, but we need 8 bits for addition and subtraction. We will see that later. So 8 bits are sufficient to reuse or to communicate the most frequently used characters. Now within this, some values take just 1 or 2 bits, some values will take 6 or 7 bits. But the point is 8 bits are sufficient and 8 bits are necessary to communicate the most frequently used characters. Fine. So the standard. Okay, so just a minute. So now the encoding will be unique. Each character will have exactly 1 binary number mapped to it. So now this function will be 1-to-1. It will not be many-to-one mapping. Now since it is 1-to-1, inverse is easy. Whenever I see this binary number, I know this will be mapping to this particular character. The inverse is also easy. So decoding is unambiguous. In the previous case, decoding is ambiguous because many characters are mapping to the same binary mapping. But now each character has a unique binary mapping. So when you see a binary number, you know which character it stands for. All right. So this solves that ambiguity problem. So in computer, the standard case is 8 bits is 1 byte. So that is my most basic chunk, most basic block. So a computer reads 8 bits at a time. It reads 1 byte at a time. Whether you are sending A or B or whether you are sending the enter key or whether you are sending backspace, whatever it is, it will take 8 bits. If it fits within 3 bits, the remaining bits will be 0. If it fits within 7 bits, the remaining bit will be 0. But everything will fit within 8 bits, not more. Fine. So 8 bits is the unit here. So in C, not only in C, in every programming language, you have something called data types. Now data types are of different kinds. Like this problem which I said earlier, within a byte, we can't do anything. Now minimally we need to use a byte. We need to use 8 bits, no matter how small the value of the character you want to set. Now, suppose I know I am sending a character, right? Characters will fit within 256 values. I don't need more than 256 values to store a character. a single character. So to store 256 different values, what is the maximum number of bits I need? 8. So I won't use more than 8 bits to send a character. But if I want to store a number, suppose if I want to send, okay, now number again there are two possibilities. Suppose if I want to send a number less than 256, how many bits I need? 8. Up to 256, up to 255. Okay, maximum number using 8 bits is 255. So if I want to send a number between 0 to 255, I will use 8 bits. But if I want to send a number, not character, if I want to send a number greater than 255, what should I do? Minimum 9 bits, right? Because 256 cannot be stored in 8 bits. 256, 257, 1000, 1 million, 1 billion, they cannot be stored in 8 bits. Using 8 bits, I can store only up to 255. Now this 255 can be treated as a number or as a character, depending on what your purpose is. Okay, but to store larger numbers, I need minimum 9 bits. Again, from 9 to, now the moment I add 1 bit, I can't stop there. I have to add an entire byte, because byte is my basic block now. So after 8, I have to go to 16. I cannot stop at 9 or 10. I have to go to 16. So I can add 1 byte at a time. Okay, so if 8 bits are not sufficient, then I need to use 16 bits. If 16 bits are not sufficient, then I need to use 32 bits. Okay, so this is what we do. So character is one data type which is usually used when in two cases. One is, say if you know you are dealing with characters, ABCD or 0, 1, 2, 3 as characters. Okay. In case you are, if you are using small numbers, very small numbers, 0 to 255. In both these cases, character is used, character data type is used, because there you don't want to use 2 bytes. 1 byte is sufficient because you are dealing with characters and you are dealing with smaller numbers. But if you know you are dealing with larger numbers, then minimum 2 bytes are sufficient. 2 bytes are necessary. So that data type is called short int. Fine. So short int has 2 bytes. 2 bytes means 16 bits, which means what is the range of values? 0 to 2 power 16 minus 1. So these many different numbers you can store in 2 bytes. Suppose now this number also has a limit. If I want to represent larger numbers, then 2 bytes are also not sufficient. Then I need to use a larger data type, that is 4 bytes. That is int. 4 bytes means 32 bits. 32 bits means the range is 0 to 2 power 32 minus 1. That's what we saw in the earlier example. 32 bytes, if everything is 0, then it is 0. If everything is 1, then 2 power 32 minus 1. Now this number also has a limit. Suppose if I want to represent much larger numbers, then it is called long int. Long int has 8 bytes. 8 bytes means 64 bits. 64 bits means the range is 0 to 2 power 64 minus 1. Okay, so usually int is sufficient for most of the practical purposes. If that is not sufficient, long int is there. Okay, if that is not sufficient, long int is there. If that is not sufficient, then we will also get into float, double, all those things we will get into later. But the main idea is for you to understand why we need bytes and why we need different data types. If I know my numbers are smaller, I will just use short int. If I know my numbers are much smaller, or if I am just dealing with characters, I will just use char. Char is nothing but an integer data type. It can be used for both cases. It can be used to handle numbers between 0 to 255, or it can also be used to deal with characters. Characters are basically numbers, right? So it is a number only. Okay. So depending on my purpose, I will choose the correct data type. That is what we do. Okay. We will enter data types a bit later, but currently understand that the point is we need chunks. We will read 1 byte at a time, not 1 bit at a time. The moment you cross 1 byte, you have to use 2 bytes. You can't use 9 bits or 10 bits. You can't use 1.5 byte or 1.1 byte. You can't use like that. You have to use one chunk of 8 bits at a time. Okay. So that is what we looked at so far. We will continue in tomorrow's class. Fine.